Hello and welcome to our discussion on hyperbolas. This is the last of our discussions on analytic geometry. We talked about circles, then we covered parabolas, then ellipses, and now we're going to finish with hyperbolas. All right, this is just a heads up to let you know there are going to be 5 classwork questions. So by the end of these videos, you should have completed all 5 of these problems. All right, so we're going to talk about characteristics. This is our objectives. Characteristics of hyperbolas, and there are basic terminology. We're going to graph hyperbolas. We're going to write equations of hyperbolas, and then we're going to write hyperbolas in general conic form from standard form. All right, so definition of a hyperbola is a set of all points such that the difference of the distances between all points and the foci is constant, which means if I take d1 minus d2, that's going to be some value, and then d3 minus d4. So from f2 focus 2 to this point of the hyperbola, minus d4, this distance from this focus to the hyperbola is going to be constant. So just to set up this graph here, I have my 2 branches of my hyperbola. I have 2 foci that are inside the branches, and then I have the distances from the foci to a hyperbola. So the difference of the distances from both foci, this is foci 1 and foci 2 here, make that look like an F. The difference of the distances is going to be constant. So d4 minus d3, d2 minus d1. We can also consider this to be the absolute value of the distances. So it doesn't matter, let's say, what order we subtract the distances from each other. That absolute value is always going to be constant. So d3 minus d4, d4 minus d3, it doesn't matter as long as we have those absolute value brackets on. The difference of those distances is always going to be constant. Okay, so let's talk about what establishes and the components of a hyperbola outside of the definition. So in a hyperbola, we have a transverse axis. The transverse axis runs through both of the vertices of the hyperbola and also the center. We have 2 branches, left and right, or up, down, depending on the orientation of the transverse axis or the hyperbola. The A value, again, is going to be the distance between the center and the vertices. We have the vertices of both branches of the hyperbola. And then, of course, we have the distances d1 and d2 that we talked about, the differences of which are going to be constant. So transverse axis, is the line which joins the vertices of the hyperbola and also runs through the center. The vertices are going to be the tips of each of the branches, so we'll call this a tip. The vertices are going to be A units from the center. So wherever that center is going to be, it doesn't always have to be at the origin. If I take A units and a horizontal transverse axis to the left and A to the right, I will end up at the vertices. So vertices are the tips of the branches of the parabola, and by tip I mean for the branch on the left there's no greater point after this point here, and then on the right branch there's no point that's less than this particular point for the vertex. Those vertices are A units from the center. All right, the center of the hyperbola is the midpoint between the vertices and the foci along the transverse axis. Remember we talked about using the midpoint formula. So now we have 2 vertices, center is between those 2 vertices. We have 2 foci, the center is a midpoint between those 2 foci. So the center of the hyperbola is the midpoint between the vertices and the foci along the transverse axis. The foci of the hyperbola lie inside, so inside of the branches, and are C units from the center. So again, we have C and C here, and this doesn't change again from the ellipse. And so you can see we have on a horizontal transverse axis, we have minus C units and plus units, so C units to the left and then C units to the right from the center, and we end up with the 2 foci. Now C can be determined as being c squared is equal to a squared plus b squared. So if you have the a value and the b value, and we haven't talked about the b value yet, you can find the c value. But note that this is different from our equation for c squared for an ellipse, because the equation for c squared for an ellipse is a squared minus b squared. So in this case, we have a change just in this value instead of negative, which is what it is for ellipses. We have a positive value, which is what it is for hyperbolas. So c squared is equal to a squared plus b squared. And again, you can find out what c squared is if you have a squared and b squared, both for ellipses and hyperbolas. All right, asymptotes are the lines which the hyperbola come close to but never touch. I call this the scaffolding of the branches of the hyperbola. All right, hyperbolas have two branches and two asymptotes. The slopes for the asymptotes are going to be plus or minus b over a, depending on the asymptote. Now please note that the slope formula b over a will change to a over b when, and we'll see this in a moment, when the transverse axis is a vertical orientation. So instead of left or right branches, we have up-down branches. So in this case, we haven't talked about b yet, but the b value, right, is something we talked about with co-vertices. But now we're going to use a b value to structure the asymptotes of the hyperbola. It's not necessarily a point on the hyperbola, but it is a reference or a marker for us to use when we're creating the equations for the asymptotes. All right, so here we have two branches. We have the asymptotes, we have the two vertices, we have the two foci, and then we have the transverse axis running through the foci, the vertices, and the center of the hyperbola. Please note also that these the branches of the asymptotes, the lines that constitute the asymptotes, also go through the center of the hyperbola, which again does not need to be the origin in an xy axis plane. All right, so here's your first classwork. So I've numbered each of the values for each of the components or parts of a hyperbola that we discussed. And so I want you to provide the sum for A, B, C, D, and E based on this diagram. So I'm going to leave this up for another moment. This brings us to our second set of classwork problems, and same thing here. So I have numbering or values for all of the parts of a hyperbola, and so I want you to find the sum of f, g, h, and I. I'm going to leave this here for a moment. Okay, so let's move on. We're going to move on. We talked about characteristics, definition, parts of a hyperbola. Now we're going to talk about how to graph hyperbolas. All right, so I'm going to go ahead and give you the form of a hyperbola, both with a horizontal transverse axis and also a vertical transverse axis. So the center of the hyperbola is located at HK. So here's my center HK. So nothing changes between centers for ellipses or circles and hyperbolas. So center here HK. With a horizontal transverse axis, you're going to have the a squared value underneath the x value and the b squared underneath the y. Now, the difference between ellipses and hyperbolas is that the a squared value for hyperbolas does not necessarily have to be the larger of the two values. What distinguishes the a value is, or the placement of the a value, is that it is associated with a term that's a positive term. So a squared is underneath the positive term, b squared is underneath the negative term. B squared can be greater than a squared in this case. So here again, the formula for a hyperbola with a horizontal transverse axis. All right, so hyperbola with a vertical transverse axis, you can see vertical transverse axis here going through the vertices and the center of the hyperbola. Now the a squared value is associated with the positive term here, but the positive term here is the y squared term. So y squared term is positive. The transverse axis is vertical. If the x squared term is the positive one, then the transverse axis is horizontal. X for horizontal values, y for vertical values. And then that again determines the placement for the a squared and the b squared values. All right, so a, as we said before, is the distance from the center of the vertices along the transverse axis. And a, again, is the denominator associated with the positive, not necessarily the largest, as in the case of the ellipses, term. All right, so here's the horizontal form for transverse axis. Here's my a value. You could consider this a negative a value. This is a positive a value. C is going to be the distance from the center in both directions to the foci along the transverse axis. And again, I gave you the formula c squared is equal to a squared plus b squared, which differs for the formula c squared is equal to a squared minus b squared. So you can see with the hyperbola where this sign is negative and this sign is positive, but for a hyperbola, this sign is positive and this sign is negative. All right, so that's the difference in the equation, at least for ellipses and hyperbolas. C value is the distance still from the center along the transverse axis to the foci. Right, b is the denominator associated with a negative term, and the b value is going to help us determine the location of the asymptotes. So we can mark the b value along what would be that line that separates the two branches and is the vertical line that runs right through the center. And we can set that up. If we want, we can march out b units from the vertex in a vertical dimension. So b units up and b units down. And then from this vertex, b units up and b units down. And then we can draw the asymptotes from there. So what we're really doing with the b value is we're using the b value as a marker from either the center or the vertices to help mark out these red points, which are going to be the points which help us determine the line which constitutes the asymptotes. And so let's talk a little bit more about that when we talk about equations for the asymptotes, which is what we're going to do now. So the slope of an asymptote with a horizontal transverse axis is going to be plus or minus b over a. So you can see here, if I am creating my line, this line should go through this blue dot. Then the slope is going to be a units to the vertex and then up b units to this point, which is one of the points on one of the asymptotes. And so we can use these 2 points to construct an equation for the line for the asymptote. So the b value here, b units up, b units down, b units up, and b units down from the vertices respectively on the two separate hyperbola branches. All right, in the case of a vertical transverse axis, then the slope is going to be a over b because the a distance is the vertical distance now. So rise over run. So my rise now is a, my run is b, and I'm still going to use the same process to mark off the point at which you're going to draw your asymptote line through both the center of the hyperbola to this point to create your asymptote. All right, so for a vertical transverse axis, then your slope will be plus or minus a over b. Plus or minus again because we have two different asymptotes running across each other through the center. All right, so we want to do a quick refresh on equations of lines using the point slope formula. So recall y minus y1 is equal to m times x minus x1. And we're going to need this when we're constructing equations of lines as we move forward in this lesson for the asymptotes for the hyperbola. So again, slope is plus or minus b over a for horizontal transverse axis, plus or minus a over b for vertical transverse axis. You're going to use the center hk for x1, y1, and then you're going to use the slope that we've gotten for the plus or minus b over a to create your equation for the line.